Cuando me digas, Alberto.
Listo, Enrique. Sí, empezamos.
Good morning, good evening, good afternoon to everybody. I have the pleasure to present Alessandro Alla, that is our speaker today. He is going to speak about the Hamilton-Jacobi-Bellman based approach for the control of PDEs. So thank you very much for accepting to participate in this seminar, and you can start when you want.
All right, thank you, Enrique, for presentation, and thanks to organize for the invitation. It's a nice, very nice opportunity. So the topic of my talk goes back to Dante talk, which was 2 weeks ago, on the approximation of Hamilton-Jacobi-Bellman equation for large dimensional problem, in particular control of PDEs. So this is a joint work, work in progress with Hugo Oliveira, which is my PhD student from PUC Rio, and Gabriele Santin from the Fondazione Bruno Kessler in Italy. Okay, so the outline of the talk, I will first recall the dynamic programming principle and its discretization. So I will mention problems that standard problems that we have in this approach. Then I will talk about radial basis functions and the Shepard approximation, and see how we can combine this radial basis approach with the dynamic programming principle in order to approximate, to compute control for PDEs. And at the end, there will be some tests that show the effectiveness of the algorithm that we are proposing. All right. So to set our problem, what we want to control an ordinary differential equations. In this case, we are dealing with the infinite horizon problem. Y is the state, U is the control, X is going to be my initial condition, and in general, I can consider this is a problem in dimension D, where we can think that we have existence and uniqueness of this problem without any problem. And since U is going to be my control, and so then this is the unknown part. What we want to do, we want to select U. We minimize a cost functional, which is defined here, and this is over the infinite horizon. So G is going to be my running cost, and lambda is going to be my discount factor. And actually, we need this term in order to get the convergence of this infinite integral. And since we want to deal with feedback control, the key ingredient is the definition of the value function, which is the infimum over all the possible controls of the cost functional. So why the value function is so important? So assuming that we are able to compute the value function, which is actually the main topic of the talk. So let's suppose for the moment that we are able to compute, or let's say to approximate the value function, then the computation of the feedback control is just really depends on the position X, and you see this is given by the argmin of this formula, where you have the running cost and you have the dynamic and you have the value function. So roughly speaking, in order to compute the feedback control, we only need to know the value function. So how can we know the value function? One characterization of the value function, which goes back to Bellman in the 60s, is the well-known dynamic programming principle. So this is an implicit characterization of the value function, where what we can learn from this formula is that we can split our control problem in 2 times. So we first run the system up to time tau, and then we correct with the best we can do, which is the value function, starting from the position at time tau, and then we minimize all over all the possible control. So this is a first characterization given by Bellman, and then from the dynamic programming principle we can derive the Hamilton-Jacobi-Bellman equations. So you see here we have this partial differential equation where all the ingredients from the control problem are inside this equation. Let's say we have the discount factor, we have the running cost, of course we have the value function, which is the unknown of this equation, and we have the dynamic of the system. This is a nonlinear PDE, which it's hard to solve analytically, and also we don't have a classical solution. So what is possible to prove here that it's possible to compute, to have existence, a uniqueness of the value function in the viscous sense. So that means that we need to have a weak solution. Then it's clear that what we want to do some numerics, and we want to approximate the value function. And among the different ways that are in the literature for the approximation of the value function, we choose the Semi-Lagrangian scheme or the direct approximation of the value of the dynamic programming principle, where you see here what we are doing. We are doing the discretization of the integral by a rectangular rule, and here we are approximating the ordinary differential equation with an explicit Euler method. Of course, this can be generalized, and you can use any other methods. For simplicity, we keep explicit Euler method here to approximate the differential equation. So you see then what we can do. We can write as a fixed point. And there are already some challenges here in this approximation. So provided that you have to solve this problem in dimension d, where d is the dimension of my differential equation. So if d is very large and you want to work with a structured grid, so the case of dimensionality comes into play. So it's basically impossible to solve this problem on a structured grid when d is larger than 5 or 6 on a standard laptop. Then we have other issues. Say, for instance, when you have a grid and then you compute the one step of the Euler method, you see that this point might not be a point of your grid. So that means that we need to perform an interpolation here in order to reconstruct this point. And also, the theoretical framework is given for without boundaries in the Hamilton-Jacobi-Bellman equation. But for numerical reason, we have to define a numerical domain, which is not natural. And also, we have to impose some boundary conditions to the problem. So again, once you do the fully discretization here, you can easily write as a fixed point, where it has been shown that this map is a contraction map. So the convergence is guaranteed for any initial condition. And then once you solve this fixed point, you can compute the feedback control, which is actually a real function of the state, where x is the current position at time tn. So the key point is the computation of the value function, and this is the standard approach on a structured grid, which has been used for many years. Then what happens if we want to increase the dimension of the problem? Imagine that we want to control a partial differential equation. If we make a discretization of the partial differential equation, let's say we have a semi-discretization in space, we end up with a large system of ODEs, which then means if we want to control this large system of ODEs, that means that the Hamilton-Jacobi-Bellman equation will have the same dimension of the system of ODEs, which is already not feasible if you have a system of dimension 5 or 6. Imagine when you discretize a PD. So this is the actual goal of this talk, is to approximate the Hamilton-Jacobi-Bellman equation in a high dimension. There are many methods nowadays. I mean, I think it's a really open research topic, and in the last 10 or 15 years, there have been lots of people contributing on this challenge. And here there is a list of methods that have been used from model order reduction, spectral methods, tensor decomposition, recently max plus algebra and neural networks. And I also want to point out that Luca Saluzzi is going to talk on another algorithm based on a tree structure algorithm for a finite horizon control problem. What we want to do in this talk is the use of radial basis function to approximate to, let's say, to use as interpolation routine. So this talk is really based on this paper by Junge and Schreiber from 2015, where they gave the idea of using a radial basis function for the dynamic programming principle. And basically, we are extending this work because they work on the low dimensional setting and structure grid. So what our aim is really to do to use high dimensional problem and unstructured grid. And so this is, I would say, the main reference where we started to think about this problem, this approach. And furthermore, what we are going to propose is a way to automatic way based on a posteriori error, an automatic way to select the radial basis function. We also provide some error estimate and a feedback reconstruction for at least a class of initial conditions. But throughout the talk, I'm going to give more details about these ideas. Okay, let me first provide some information about radial basis function. So this is at the moment a standard interpolation method. So imagine that we have some node, some function we want to interpolate, and here we are going to use a special kind of function, which are radial basis function, where you see that you take positive values in R, and you have a parameter which is called the shape parameter. Actually, this shape parameter is crucial because that really modifies the base that you're choosing. Here there is an example when dealing with this bundle radial basis function. You see, if you have on the left you have a flatter radial base, and if you have a larger sigma, you have a spiker radial base. So this parameter is really important to select in order to get the results. I mean, it really changed the quality of the results. And the way that we compute the CI terms here is given by standard linear system. Actually, for the purpose of our talk, we are going to use the Shepard approximation, which is instead again given by radial basis. So you see that here we have f of xi, which are the f evaluated in our node of the grid, times this base, which are now given by this formula, where you see that we are kind of normalize the basis here. And the first big difference is that we don't solve a linear system to compute this approximation, but we just have to do a computation matrix times vectors. Furthermore, we have some other nice interesting properties, such that the bases here in the Shepard approximation have a compact support, and actually the support really depends on the shape parameter. You see that each base here is in a ball where the center is given by the node xi and the radius is 1 over sigma. Then we also have that the sum of all the bases is 1, and the computational domain then is given by the union of all these balls. Then we can exploit the fact that these bases have a compact support, because as you see that this is a radial basis. So what we need to compute? We need to compute this distance. And since we have a compact support, we do not have to compute the distance for any point, but just for the points that are closer within a radius 1 over sigma. That means that this matrix is gonna be sparse, and that's also computationally has some positive consequence in the computational from the computational point of view. So since this method can be used for any kind of grid, we don't have, let's say, a standard distance. We can use the field distance, which is the minimum, or let's say, which is the minimum of the terms of your node, and the maximum of the around the greatest ball, which does not, the greatest hole inside our computational domain. Or one can consider the separation distance, which is easier to compute, which is actually the actual distance between two nodes inside the grid, inside the domain. In their paper, Jung and Schreiber, they also derive some error estimate for the Shepard approximation, and actually they extended an existing proof where the function now is Lipschitz continuous, which is actually our case because the value function is usually Lipschitz continuous. So they extended to this Shepard approximation error for a Lipschitz continuous function. And you see that the error estimate depends on the field distance. So that means that provided that the field distance is going to 0, this approximation is going to 0. Now we want to use this Shepard approximation inside our value iteration scheme, and formally we only need to replace the linear interpolation operator with the Shepard approximation. So you see that at least from a formal point of view, there is no difference. We are just using a different operator to approximate the value function in this point. Actually, we know that this operator is still a contraction because the Shepard operator has norm 1. So this is possible to prove that we have a contraction, and since we have a contraction, we have a fixed point. So we have a convergence for our method, and also the error estimate. Again, now that depends on the field distance over delta t. This is a standard error estimate for a semi-Lagrangian scheme, and where h basically replace the standard delta x that one can have in equidistant grid. Then also the computation of the feedback control is again formally the same. The only difference that we are again using the Shepard operator. Now, if you see this error estimate, the error estimate depends on h, which is actually not trivial to compute, if not impossible to compute for high-dimensional problem. So that means that we are essentially covering the whole computational domain to get that h is going to 0. And I mean, if H is really going to 0, we go back to the cards of dimensionality. And also, what we need to exploit is the fact that the Shepard approximation really works in high dimension and for unstructured grids. So what we are going to propose is how to generate the unstructured mesh, how to select the shape parameter inside the radial basis or the Shepard approximation. We have, let's say, a first sketch of some error estimates, and then to show how it works for control of the PDEs. So first problem is how to generate a mesh. Of course, we have lots of ways to generate a mesh. Sorry, yeah, I've done some. Okay. What exactly you don't want that happens when you're doing a talk? Some water goes to my iPad. Okay. Okay. Anyway, so how to generate a mesh? Okay. First thing that you can do is to make an equidistribution. Where the pro is that you can cover the space, but of course this is not feasible when you deal with a high-dimensional problem. So the high-dimensional problem is something that order 1,000 or larger in my what I have in mind. If we do, if we make a random set, we take just a random set of points. This is easy to generate, but the distribution can be very irregular. That means that the field distance might decrease very, very slowly in order to cover the whole space. In general, what we want a trade-off between a reasonable size of the grid and the part of the domain that you want to cover. And also is well known that for a d-dimensional problem, the H distance decay very, very slow. Is n to the 1 over d. So it's very hard. I mean, if we want to cover the whole space, but instead we can try to localize the full space. In fact, if we think about our discretization, what we have here. So if we have some node xj, what we want to do, we want to compute the interpolation operator in xj plus delta t of f. So that means that provided xj, the only other point that we want to compute is where we want to compute the interpolation is along the trajectory, because this is one step of the Euler method. So what we can do, we can drive a grid which is driven by the dynamic of the problem. So this is actually the key fact which helps to localize in the high-dimensional problem, to localize and to select the grid points. So to do that, what we need to compute, we need to fix a time step, a maximum number of times instance, a number of initial conditions, and a number of controls. In this way, we can compute trajectory for any pair. So given an initial condition and a constant control, so we suppose the control is fixed along the time, we can simulate the differential equation, and we store all the trajectory. So given initial condition and the fixed control, we store this trajectory. Okay, so then our grid will be the union between all the initial conditions that we have chosen and all the discrete control that we have chosen. So this is the union, and this will be actually our computational grid. Of course, our aim is not to fill the full numerical domain, but to provide points along trajectory of interest, which is actually where we want to compute the feedback control. So the crucial information here is actually given by the number of control, number of time steps, delta t, and we can actually derive some error estimates, or at least some properties for the mesh. So suppose that f is bounded, which is a totally reasonable assumption, especially when we want to use we use this the dynamic programming principle. So that means that the distance between a point of the grid and any other point, the maximum distance, is bounded by the maximum of the function times delta t. And actually, if we suppose that f is Lipschitz continuous with respect to the state and the control, we can actually bound the distance. We can have a, let's say, a more interesting bound of a point of the grid and another trajectory. For another trajectory is given here. That means that is given by initial condition x0, a control u, and a time step delta t. Whereas, let's say that a point in our grid is given by x bar, delta t bar, and u bar. What you can see here, that we can really control the distance. So again, this is, let's say, a way to replace the standard delta x in an equidistant framework, and we replace with this distance. So along the trajectory, so we are, let's say, we can think that we are in a tube around the trajectory, and we can get an estimate. And actually, the interesting thing that we can actually play with the parameters that are involved in the choose when we choose the grid. So you see that we can deal with delta t, with the initial condition and the control. So this might go to 0, dealing with these three terms. And actually here you see an exponential term. This is due to the lemma, the Gromwell lemma. So essentially, this is again a way to replace the field distance or separation distance in our context. Now I want to focus on the selection of the shape parameter. This is, let's say, an hard problem in radial basis function community. Already Fassauer and also Jung and Schreiber, they discuss about that. Actually, in their paper, Jung and Schreiber, they did not focus on the selection of the shape parameter. They just fix a priori the parameter. Usually, people try and use an error procedure to select sigma. There are also lots of algorithms using cross-validation and maximum likelihood estimation to select sigma. But in our case, we have a non-standard problem because our approximation is changing at each iteration. So let's think about the standard interpolation where we have x and f of x. They are both given. In our case, we have x and v of x, and v is v of k. So that means that at each iteration, the value function is changing. So it's not possible to apply cross-validation or standard procedure. So what we are going to propose here is to link sigma to some given parameter, a known parameter at the moment, theta greater than 0, and our local field distance, so to say. And the way that we actually deal is using the separation distance, which is easy to compute in any dimension. And in order to compute sigma, now qx, so the separation distance is given, is computable. So we need to compute theta. How can we select theta? We can actually minimize, given a set of admissible parameters for theta, we can minimize the residual. The residual is actually, you see, once you compute the fixed point for a given theta, you see this is the residual of the fixed point, and the minimum achieved from the residual is going to give my selection of the shape of my shape parameter. So we are moving. We are using optimization method a posteriori, because I mean the residual here does not need the knowledge of the exact solution. And so we have this optimization problem. This might be computed by comparison. Say that we want to discretize the set of parameters, and we just check we compute the value function for all the given parameters, and we select theta such that minimize the residual. Or we can use, for instance, a gradient method where we replace the derivative by the finite difference. So both methods we are going to show that they work, and actually we prefer to use the comparison method, because the amount of value iteration that we need to compute is actually smaller than here the amount that we need to perform to use a gradient method. So another important thing is how to compute the interval for the shape parameter, theta min and theta max. And actually, using the error estimate between the distance of a point of the grid and a point outside of the grid, we know that the distance here is less or equal the maximum f times delta t, which is actually less or equal 1/sigma, because we know that this point is going to be the ball with a center x and the radius 1/sigma. So that means that here we also have an upper bound for theta max, and we also know that theta can be, we can just select theta larger than 0. So in this way, I mean, we also know how to select and where to compute the shape parameter. And since we are working on a compact set, the minimum is guaranteed. Concerning the error estimate, let's go here. So the difference of the value function now, so the error that we have in the discrete approximation of the value function as the same, let's say, it's same kind of standard error for Semi-Lagrangian, but now we are able to estimate in our context the distance that we have here. And again, you see that this error might go to 0 if delta t bar is going the direction of delta t tilde. Also, the initial condition is close to x bar and the set of controls. So at least we have a way to show that this error is decreasing. The algorithm is summarized here. So basically, here there are two ways to compute the parameter. This is the residual. So either we do by comparison. So that means that for any theta in the discrete set of parameters, we compute the value function, or we really perform the gradient method, which means that at each iteration, we need to know v of theta and v of theta plus a perturbation, which we need to compute the approximation of the derivative. Let's see some tests. I still have 10 minutes more or less, right?
Yes. Okay. Yeah.
Okay. So first test, of course, is a low-dimensional problem. Why we choose this problem is because we know the exact value function in this problem, so we can compute the error and compare with standard equidistant grid and linear interpolation. So what we are going to do here is the minimum time problem, where this is where we want to reach for a given initial condition, we want to reach the target 0 in minimum time. So for this problem, the exact solution is actually the distant function, and this is the Eikonal equation. So we are going to use this Weinrad radial basis function, and we compute the error with respect to the infinite knot. So actually, in order to compare our approach, what we do, we use a relative error, which is based on our approximation, where theta bar is given by the argmin of the residual, and we compute the actual error, where theta is actually the real minimum, not the one that comes from the residual, but the actual minimum, since we know the exact value function. So here is a picture of how the residual behaves. So you see here that if we start having a large parameter set, at a certain point it's constant. What we have done here, we started with a coarse discretization of the parameter set, and then we did a finer approximation, and actually even finer, to get a minimum. So here, so this is the plot of the residual actually with respect to theta. So here is the actual error. So the error where we consider v of theta minus v star. So this is from the fixed point, and this is the actual error. And you see how the error behaves is different according to the number of points. And here I'm working with a standard equidistant grid. I'm in a two-dimensional domain, so it's not a problem to work on with an equidistant grid. And we also see the error decay when having our approach, which is based on the residual, and the actual error based on the knowledge of the exact value function. So here there are some numbers. What is interesting to see is that in both cases, of course, h over theta, which is the terms which appears in the error estimate, is going to 0 when decreasing h. This is the plot of the value function. Actually, this is the Kruskov transform of the exact solution. Here, this is the exact solution. This is the approximate solution. And this is the absolute difference between the computed one and the exact solution. So in this case, this is bounded by 0.005, I would say. And here there is also a table when using the gradient method. Actually, computationally, this is way more expensive. And also the gain that we have here in the error is very little. So we decided to drop the use of the gradient method, and we kept working with just a comparison to compute the shape parameter. So now we do a second test when using the random grid. So again, since we are working with a two-dimensional problem, this is still possible. And to generate and try to cover well the space, we took 4,000 random points, and then we cluster using k-means in order to give kind of structure, but still it's an unstructured grid. And you see how different grid we have with different number of points. And from the picture, it's already clear that the field distance here is decreasing, increasing the number of points. Again, we show here the residual, the actual error, and here the error that we computed with our a posteriori approach, and the actual error with the exact knowledge of the solution. of course, I mean, it's clear that the red line, it's going to be a lower bound, actually an upper bound for the approximation. But you see that in this case, we are very, very close to the solution that we might achieve with the best shape parameter. Then here we have the 3D plot. I mean, this is not so easy to plot since it's scattered. Here, this is the error behavior, so the absolute difference. Of course, we start to lose something having this kind of grid, but nevertheless, the error is below 10 to the -1 here. And then we want to show how it works with the dynamic grid. I mean, the grid driven by the dynamic of the problem. So we choose a parameter, and you see how, I mean, you can recognize the trajectories here. And we have 3 different settings in order to decrease the field distance. And again, here we have the residual. And I would say that the interesting part is that the actual error and the hour error, which again is based on the use of the residual, they are very close, and they are getting closer when decreasing the field distance. Also, the tables here, I mean, the quantity h over theta. Here, in this case, I can easily talk about h distance because it's in a low-dimensional setting. So we can see that here it's decreasing. From the feedback reconstruction, so you see that all the methods, so here we are also comparing with the standard linear approximation. The 3 examples is Equidistant grid and Shepard, random grid and Shepard, and the grid driven by the dynamics and Shepard. And you see that all cases we are reaching the target, which is 0. We have a different control. And the interesting part is that, of course, with a linear interpolation, this is the best we can do. I mean, the cost function has the lower result. But with our approach, which is driven by the grid driven by the trajectory, we are not so far from the other. So of course, it's as I said, it's a trade-off on what we can gain from the dimensional point of view, and from what we can lose from accuracy point of view. So now let's go to the high-dimensional problem. So this is the control of the linear advection equation. And actually, the control is bilinear control. You see that this is y times u. And when we discretize here, we have a large linear system of these, whose dimension in this case is more than 10,000. What we want to achieve from our control problem is that we want to steer the solution to 0. So this is the cost function that we are going to minimize. Here, this is a plot at time equal 5, so for a large horizon. So you see, this is the uncontrolled behavior, and this is the controlled behavior. So it's easy to see. Of course, I mean, here we have some problem with the diffusivity of the upwind scheme, but nevertheless, we can see that the control problem goes to 0 faster than the uncontrolled problem. This is the optimal control that we have computed. And I think it's also relevant that this initial condition that we have chosen is not in our grid. So to generate our grid, we choose this kind of initial condition multiplied by 0.5 and 1. So we keep the same class of initial condition, but we are using an initial condition which is not in our grid setting. And here this is the evolution of the cost function for the 3 initial conditions. So let's say that here we have the sign multiplication. Here it's 0.5 sine, and here it's 0.75. In all the cases, we can see the difference between the evaluation of the cost function for the uncontrolled and for the control case. we are always lower than the control case, and that's what we want to achieve. And the other important information is that to compute the trajectory, we do not have to update the value function. The value function is computed once for any initial condition, or at least I like to say for a class of initial condition, and then online we just need to compute the feedback and reconstruction for a different initial condition. And let's also show a nonlinear problem. So here we have a parabolic problem with a polynomial nonlinearity. This problem actually from a control point of view is very interesting, because the uncontrolled solution is reaching the unstable equilibrium, which is 1. And what we want to do from a control point of view, we want to steer the solution to the unstable, the solution is going to the stable equilibrium, which is 1. What we want to do, we want to steer the solution to the unstable equilibrium, which is 0. After discretization, here we have a problem in dimension 961, and this is the cost function that we want to minimize. As I said, this is the uncontrolled behavior for a large time. So this is the equilibrium that it is reached, and this is the controller solution, which is going to 0, as you can see. The residual is really complex inside this parameter range, so it's easy to see that we have a minimum. And this is the behavior of the control. This is actually very standard way behavior. I mean, it's really pushing at the beginning, and then once you reach the desired configuration, it's rather stable. And running cost and cost functional for 3 different initial conditions. It's clear the difference between the control and the uncontrolled problem. And also, since we are dealing with the feedback control, we wanted to check the robustness of our approach according to perturbance or disturbation of the system. So that means that for any initial condition, we are applying some random noise. And so the uncontrolled behavior, you see that now it's disturbed by this random noise, and this is the controlled solution. I mean, it's clear that we have some noise, but nevertheless we are able to steer the solution, and this is also confirmed by the evaluation of in this case this is the running cost. Okay, to conclude, what I presented today is a new way to combine Shepard approximation and control problem for a high-dimensional problem. An algorithm that is able a posteriori to select the shape parameter, and also a new way to generate unstructured meshes. What is interesting in the future is also to apply to use polyiteration in this setting, to extend this work, this method for semi-Lagrangian scheme, and maybe combine model of the reduction also to speed the interpolation part. And with that, I would like to thank you all for your attention.
Okay, thank you very much for this very interesting talk. And we have now time for some questions or comments. Is there any comment? Okay, Pedro González
has a question.
Okay.
Can I proceed now?
Yes.
Okay, thank you. Well, thank you very much. Really very nice talk. Very, very nice.
Thank you.
Well, as far as I understand, you're changing 2 basic concepts of radial basis function. One is the concept of field distance. You are changing the standard concept of field distance by local field distance, no?
Exactly.
And the other one is, since you're using a Lagrangian approach, the concept of a shape parameter is also changed. I mean, you cannot use cross-validation or whatever, but you have to make an optimization problem.
Yes.
Well, one question is, how do these compare, these local field distance, how do these compare to the standard field distance? Is more or less the same size, or?
I mean, for high dimensional
Yes.
problem, it's there is no way to make a comparison, right? Because I mean, field distance means that you want to cover the whole space. And in a high-dimensional problem, it's I mean, the problem for ages of this approach was still it's the Carso dimensionality. If you want to cover the whole space, there is no way to do that. And the field distance means that you want to cover the whole space.
Okay.
So we are actually really.
Just one more question, two more questions. You use Wendland radial basis function. Have you been using another kind of RBF? Why Wendland?
Because in the original paper by Jung and Schreiber, they used Weinblatt, and then we kept using Weinblatt. But I would say that this approach is quite general, so maybe we can also use, but we didn't try another radial basis function.
Okay, because you have exponential Gaussians.
Yes, but Gaussian maybe, yeah.
There's multi-quadratic, hybrid radial basis function. So
yeah, but I mean, as of course, I'm not expert on radial basis functions, but what I could understand, if you find your radial basis function which is working, I mean, you can be happy already.
Okay, and the last question is, what about the numerical complexity? Which is the more expensive part of this algorithm?
Of course, it's the computation of the fixed point. So the computation of the fixed point. So what we are really doing for the fixed point is to compute many value iteration, right, for any different parameter. Okay. Plus, that means that each times that we need to to compute to approximate this high dimensional problem. And also, if you see here the CPU for this problem, which is now 961, right? And the computational time here, this is a larger problem. This is faster. This is because of the PDE. This is linear, so it's easier. It's faster. Although I guess, yeah, we can use. I mean, here we are using an implicit error scheme with a Newton iteration, and I guess here if we use a Jacobian-free Newton-Krylov method, I mean, we can really speed up also this approximation. But I mean, the most expensive part is for sure the fixed point.
Okay, I think that's all. Thank you very much, and very nice talk.
Thank you.
Thank you.
Thank you. Any other question? Is there any other comment or question? Okay, I have a question, a general question. In fact, can you say something on the constraints, on the possible constraints of the control? I mean, what can you do in that case?
So here, let me go. Yeah, maybe I did not. Yes. Let me go. For instance, here. So this is usually a compact set, and what we do again here also we do by comparison. I mean, you can also use some free derivative optimization routine to compute this minimization, but at the end of the day, the comparison is faster and reliable, in my opinion. Does it reply to your question?
Yes, yes. In fact, my question is in regards of all the elements of the proof that you have, of the experiences that you have presented, is the presence of a serious constraint determinant for your work?
Well, I mean, as soon as you have a minimizer, I mean, that you can prove that you have a minimizer, I would say that it's okay. And usually what we do, we put compact set, so it's guaranteed that you have a minimizer.
And another question of the same kind: when did you perform any experience where the Hamilton-Jacobi is regularized with an artificial viscosity term? I mean, have you tried to solve not exactly the Hamilton-Jacobi equation, but an approximation performed by a viscosity solution or something like this?
So actually, if you go into the setting of stochastic control, what you have an Hamilton-Jacobi-Bellman equation where you also have this second order derivative. So there are for sure, I mean, the literature in that direction as well. But I mean, the use of here the viscosity term to approximate the Hamilton-Jacobi-Bellman equation, no, I have no experience on that.
Okay.
Yes,
well,
that may regularize for sure, but the key point here is not that it's hard to approximate this let's say non-regular function. The key point is really the dimension of the problem. From my point of view.
Okay, thank you very much. So, well, we are going to stop now, and I thank you again for your participation.
Thank you.
And I thank all the audience for their participation too, and see you next week. Bye-bye.
Ciao, ciao, obrigado.
Goodbye.
Okay. Thank you. Goodbye.
Bye, Alessandro.
Thank you. Bye-bye.
Bye-bye.